Welcome to Chapter 15 of the AEON-CASIMIR Dossier, where we dive into the advanced science of thermal management and entropy control in metric-engineered propulsion systems. Building on the foundation of energy stability from the previous chapter, we now confront the next unavoidable constraint: how to manage heat, entropy, flow, and irreversibility in systems that cannot simply expel heat like classical vehicles. This chapter is rich in equations and scientific rigor, setting the stage for a new paradigm in thermal management, one that leverages the very fabric of spacetime. The objective of this chapter is clear. All propulsion systems ultimately fail due to entropy accumulation. While classical vehicles manage heat by expelling it, metric-engineered craft like those in the AEON-CASIMIR program cannot rely on exhaust without disrupting the delicate coherence of spacetime curvature. Here, we establish how AEON-CASIMIR manages heat, entropy, and irreversibility without radiators, exhaust, or escalating thermal signatures. This approach is essential for maintaining stealth, efficiency, and operational integrity in advanced propulsion systems. In AEON-CASIMIR systems, most of the work performed is geometric, not dissipative. Unlike classical systems where heat is a direct byproduct of energy conversion, here, heat is merely a symptom of deeper processes. The majority of energy is invested in manipulating spacetime itself, rather than being lost as waste heat. This means the traditional equation Q equals delta E, W is overshadowed by the metric work integral, where Q is much less than the metric work. As a result, thermal management shifts focus from cooling to routing entropy effectively. Let's compare classical and metric work. In classical systems, heat is managed by removing it from the system, but in metric-engineered craft, work is performed directly on spacetime. The metric work equation, W, metric equals integral T, mu nu deltag, mu nu dV, highlights that energy is used to manipulate the geometry of spacetime, not just matter. This fundamental difference means that the heat produced, Q, is negligible compared to the metric work done, fundamentally altering how thermal management must be approached. In AEON-CASIMIR systems, entropy is not just an inevitable byproduct, it is a quantity to be actively managed. Entropy density is defined as S equals S divided by V, and the total entropy balance is governed by the equation ds divided by dt equals S gen plus S flow. The key operational principle is to ensure that the entropy flow out of the system is much greater than the entropy generated internally. This is achieved by exporting entropy into vacuum modes and curvature degrees of freedom, rather than into matter, fundamentally changing the way thermal stability is maintained. A revolutionary aspect of AEON-CASIMIR's thermal management is the export of entropy into vacuum modes and curvature degrees of freedom. Instead of dumping heat into the environment, entropy is routed into the structure of spacetime itself. This process prevents the accumulation of entropy in matter, maintaining system stability and stealth. By leveraging the properties of the vacuum, AEON-CASIMIR achieves a level of thermal control unattainable by conventional means. Electromagnetic EM fields in AEON-CASIMIR systems act as conveyors of entropy. The radiative entropy flux is given by S psi EM equals 4/3 P divided by T, but instead of radiating entropy isotropically, the system phase cycles EM fields, shifts entropy spectrally, and reabsorbs coherence-preserving modes. This means entropy is redistributed within the system, rather than emitted, preserving both energy and stealth. The result is a highly efficient internal entropy cycling mechanism. AEON-CASIMIR's approach to EM entropy involves phase cycling and spectral shifting. By carefully controlling the phases and frequencies of EM fields, entropy is moved into modes that can be reabsorbed or redirected, rather than being lost as waste heat. This preserves coherence and prevents detectable emissions, a crucial advantage for advanced propulsion systems operating in sensitive environments. Plasma rings within the AEON-CASIMIR craft serve as dynamic thermal buffers. These plasma structures act as heat sinks, entropy mixers, and phase randomizers. The entropy of the plasma is governed by SP equals NK line T, 3/2 N, and controlled turbulence allows the system to absorb entropy without causing temperature spikes. Magnetic confinement ensures that the ratio of thermal to magnetic pressure, beta, remains below unity, maintaining stability and preventing runaway heating. The use of controlled turbulence within plasma rings is a sophisticated method for entropy absorption. By carefully managing the level of turbulence, The system can absorb large amounts of entropy without causing dangerous temperature spikes. This is achieved through precise magnetic confinement, which keeps the plasma stable and ensures that thermal pressure never exceeds magnetic pressure. This balance is critical for maintaining the integrity of the thermal buffer. CASIMIR cavities within the AEON-CASIMIR craft function as entropy reservoirs. These systems absorb entropy by varying the vacuum boundary states, allowing for a shift in vacuum entropy without increasing temperature. The key insight is that the vacuum can act as an entropy sink, decoupled from the thermal mass of the system. This enables the craft to store or dissipate entropy in a way that does not compromise its operational stealth or efficiency. The ability of the vacuum to absorb entropy without a corresponding increase in temperature is a cornerstone of AEON-CASIMIR's thermal management. By leveraging CASIMIR cavities, the system can offload entropy into the vacuum, effectively decoupling entropy management from the thermal mass of the craft. This approach provides a stealthy and efficient means of maintaining operational stability, even under high-energy loads. Spacetime itself possesses entropy, as described by the Bekenstein-Hawking relation S equals Ka divided by 4L P 2. In AEON-CASIMIR systems, small curvature perturbations allow entropy to be transferred into geometric degrees of freedom. This means entropy can be diluted across an expanding metric volume, preventing the formation of horizons and ensuring that entropy remains bounded. This process is fundamental to maintaining the long-term stability of metric-engineered craft. By allowing entropy to be transferred into the geometric degrees of freedom of spacetime, AEON-CASIMIR systems can dilute entropy across an expanding metric volume. This prevents the concentration of entropy that could lead to instability or horizon formation. The result is a robust and resilient thermal management strategy that leverages the very structure of the universe. Time dilation is not just a relativistic curiosity, it's a practical tool for thermal management in AEON-CASIMIR systems. By locally reducing the proper time interval, dTau equals square root g 00 dt, thermal processes slow down, the rate of entropy generation drops, and the coherence length increases. This temporal engineering allows the system to manage heat and entropy at a fundamental level, extending operational windows and enhancing stability. By engineering the flow of time within specific regions of the craft, AEON-CASIMIR systems can slow down thermal processes and reduce entropy generation. This approach not only extends the operational lifespan of critical components, but also enhances the overall coherence and stability of the system. Temporal engineering is a powerful tool in the arsenal of advanced thermal management. Thermal noise is a major driver of decoherence in quantum systems. The decoherence rate is proportional to kT delta E, meaning that higher temperatures and energy differences accelerate the loss of coherence. By controlling entropy flow, AEON-CASIMIR systems can extend coherence times, suppress quantum noise, and maintain vacuum stability. This is essential for the reliable operation of advanced propulsion and control systems. Quantum coherence is vital for the advanced control systems in AEON-CASIMIR craft. By managing entropy flow and minimizing thermal noise, the system can maintain long coherence times and suppress unwanted quantum fluctuations. This ensures that the craft remains stable and responsive, even under demanding operational conditions. Traditional radiators and exhaust systems are not viable in metric-engineered craft. Radiators emit detectable signatures, break stealth, and disrupt metric uniformity. Instead, AEON-CASIMIR employs internal entropy cycling, vacuum mode dumping, and curvature expansion to manage heat. The result is a system with an effectively zero thermal signature. Sigma, thermal, is approximately equal to 0, maintaining both operational secrecy and efficiency. AEON-CASIMIR's internal entropy cycling is a sophisticated process that keeps entropy moving within the system rather than allowing it to escape as heat. By continuously cycling entropy through various internal modes, including EM fields, plasma, and vacuum states, the system maintains thermal equilibrium without external emissions. This approach is key to the craft's stealth and operational longevity. Vacuum mode dumping is a unique feature of AEON-CASIMIR's thermal management. By exporting entropy into the vacuum, the system avoids the need for radiators or exhaust. This process leverages the properties of the quantum vacuum, allowing the craft to remain undetectable while maintaining thermal balance. It's a prime example of how advanced physics can be harnessed for practical engineering solutions. Curvature expansion is another method used to manage heat in AEON-CASIMIR systems. By expanding the metric volume, entropy is diluted and distributed across a larger region of spacetime. This prevents the buildup of heat and maintains the uniformity of the system's metric structure. It's a subtle but powerful way to control thermal dynamics without traditional cooling methods. Suppressing the thermal signature is critical for stealth operations. AEON-CASIMIR's approach ensures that the thermal emission coefficient, sigma, thermal, is effectively zero. By keeping all entropy and heat within the system or exporting it into non-detectable modes, the craft remains invisible to conventional thermal sensors. This capability is a direct result of advanced entropy management techniques. Uncontrolled entropy can lead to several failure modes in AEON-CASIMIR systems. These include plasma decoherence, Casimir boundary noise, and metric instability. To prevent these outcomes, the system enforces the condition dt is less than S, max, ensuring that entropy never exceeds safe operational limits. Continuous monitoring and control are essential to maintain system integrity. Maintaining control over entropy flow is vital to prevent system instability. AEON-CASIMIR systems are designed to keep entropy generation and flow within strict limits, using real-time monitoring and adaptive control mechanisms. This proactive approach ensures that the craft remains stable and operational, even in challenging conditions. In extreme situations, AEON-CASIMIR systems can perform an emergency entropy dump. This involves relaxing the metric curvature, increasing plasma turbulence, and briefly radiating EM entropy. Once the emergency is resolved, the system returns to its baseline state. This capability provides a safety net, ensuring that the craft can recover from unexpected entropy spikes without permanent damage. After an emergency entropy dump, the AEON-CASIMIR system is designed to quickly return to its normal operational state. This rapid recovery is made possible by the system's robust control architecture and the inherent flexibility of its thermal management strategies. The ability to handle and recover from entropy spikes is a testament to the resilience of the AEON-CASIMIR design. Thermal management and entropy control are inseparable from energy stability. Chapter 14 established the principles of energy stability, which are essential for effective entropy management. In turn, controlling entropy ensures that energy remains usable and the system operates efficiently. This integration is at the heart of AEON-CASIMIR's advanced propulsion and control architecture. The relationship between energy stability and entropy control is mutually reinforcing. Without energy stability, entropy cannot be effectively managed. Conversely, without entropy control, energy quickly becomes unusable. AEON-CASIMIR's design philosophy recognizes this interdependence, ensuring that both aspects are addressed in tandem for optimal performance. A key principle of AEON-CASIMIR's thermal management is that heat is not expelled from the system, it is transformed. Through a combination of entropy, routing, vacuum absorption, and geometric manipulation, the system ensures that heat never accumulates where it could cause harm. This approach is fundamentally different from traditional cooling methods and is central to the craft's advanced capabilities. Entropy cannot be eliminated, but it can be routed away from critical areas. AEON-CASIMIR systems are designed to direct entropy into regions where it poses no threat to operational stability. This routing is achieved through a combination of internal cycling, vacuum dumping, and metric manipulation, ensuring that entropy never accumulates in sensitive components. In AEON-CASIMIR systems, both the vacuum and the geometry of spacetime are treated as thermal resources. By leveraging these aspects, the craft can manage entropy and heat in ways that are impossible with conventional materials. This innovative approach is a hallmark of metric-engineered propulsion and control systems. Time itself is used as a control parameter in AEON-CASIMIR's thermal management. By manipulating the flow of time within the system, thermal processes can be slowed or accelerated as needed. This level of control is unprecedented and allows for fine-tuned management of entropy and heat, further enhancing the craft's performance and resilience. The ultimate goal of AEON-CASIMIR's thermal management is not to cool the system, but to prevent entropy from forming where it matters. By intervening at the earliest stages of energy, conversion, and work, the system ensures that entropy is never allowed to accumulate in critical areas. This proactive approach is key to maintaining long-term operational stability. To summarize, AEON-CASIMIR's approach to thermal management and entropy control is built on several key principles. Heat is transformed, not expelled. Entropy is routed, not eliminated. The vacuum and geometry are used as thermal resources, and time itself is a control parameter. These principles set AEON-CASIMIR apart from conventional systems and enable its advanced capabilities. Throughout this chapter, we have maintained a high level of scientific rigor, using advanced equations and concepts to describe the processes at work. From the metric work integral to the Bekenstein-Hawking entropy relation, every aspect of AEON-CASIMIR's thermal management is grounded in established physics, ensuring both reliability and credibility. The operational advantages of AEON-CASIMIR's approach are significant. By eliminating external heat signatures, maintaining internal stability, and enabling rapid recovery from entropy spikes, the system offers unmatched stealth, efficiency, and resilience. These benefits are critical for advanced propulsion and control applications in demanding environments. Stealth and security are paramount in AEON-CASIMIR's design. By avoiding detectable thermal emissions and maintaining metric uniformity, the craft can operate undetected in hostile or sensitive environments. This capability is a direct result of the advanced entropy management strategies outlined in this chapter. Maintaining long-term system integrity is a core goal of AEON-CASIMIR's thermal management. By preventing entropy accumulation and ensuring rapid recovery from disturbances, the system is built for longevity and reliability. This focus on integrity ensures that the craft can perform its mission over extended periods without degradation. The advanced propulsion and control capabilities of AEON-CASIMIR craft are made possible by its sophisticated thermal management and entropy control systems. By integrating these functions at a fundamental level, the craft achieves performance levels that are unattainable with conventional technology. This integration is the hallmark of metric-engineered systems. Every aspect of AEON-CASIMIR's thermal management is grounded in scientific principles. From quantum field theory to general relativity, this scientific foundation ensures that the system is both innovative and robust, capable of meeting the demands of modern propulsion and control applications. Looking ahead, the principles established in this chapter open the door to even more advanced forms of thermal management and entropy control. As our understanding of spacetime and quantum fields deepens, new opportunities will arise for further enhancing the performance and capabilities of metric-engineered systems like AEON-CASIMIR. In conclusion, Chapter 15 of the AEON-CASIMIR Dossier has established a new paradigm for thermal management and entropy control in advanced propulsion systems. By transforming heat, routing entropy, leveraging vacuum and geometry, and using time as a control parameter, AEON-CASIMIR achieves unmatched performance, stealth, and reliability. These innovations set the stage for the next generation of metric-engineered craft. Let's recap the core concepts. AEON-CASIMIR does not cool systems in the traditional sense. Instead, it prevents entropy from forming where it matters, routes it into harmless modes, and uses the fabric of spacetime itself as a thermal resource. This chapter's insights are essential for anyone seeking to understand or develop next-generation propulsion and control systems. Thank you for exploring Chapter 15 of the AEON-CASIMIR Dossier. The advanced techniques described here represent the cutting edge of thermal management and entropy control. As we continue to push the boundaries of science and engineering, these principles will guide the development of ever more capable and resilient systems. Stay tuned for future chapters as we delve deeper into the mysteries and possibilities of metric-engineered propulsion.